Chapter 2, Section 6, Digging Deeper, Interpreting Geologic History, Geologic Events and Processes. In the Investigate, you studied how scientists determine the ages of rock layers. You did this by using models and cross-sections. By discussing your interpretations of a geologic cross-section of an area, you most likely agreed on a single, well-supported claim about the ages of its rock layers. It is important for geologists to know the age of the rock layers. Most areas of Earth's crust have a long and often complex geologic history. Many kinds of geologic events can occur. Many kinds of geologic processes can shape the geologic history of an area. You have read about many of these in previous sections. Here are some important ones: deposition, erosion, folding, faulting, uplift, subsidence, igneous intrusion, volcanism, metamorphism, changes in sea level, and climate change. The only processes in this list above that you have not yet looked at in detail are uplift and subsidence. Local areas of Earth's crust can be slowly raised, uplift, by large-scale forces acting within the Earth. They can also be lowered, subsidence. Vertical changes in elevation can range from meters to kilometers. Much of uplift and subsidence is caused by the movement of Earth's lithospheric plates. However, it can also be caused just by changes in the temperature of the rocks. When rocks cool, they contract. That causes subsidence. When rocks are heated, they expand. That causes uplift. The degree of contraction and expansion is small. However, great thicknesses of rock are affected, kilometers to tens of kilometers. As a result, uplift and subsidence of Earth's surface caused in this way can amount to hundreds of meters. Basic geologic principles. Geologists make geologic maps of areas of bedrock. The surface geology shown in these maps comes from data gathered from a variety of sources. These include topographic maps, satellite images, and boreholes. Hold on, did we miss a figure? Nope, we didn't miss any figure. Okay, this is the first figure. So figure one shows that in a series of rock layers, the oldest rocks are usually found on the bottom, while the youngest rocks are on the top. Basic geologic principles. Geologists make geologic maps of areas of bedrock. The surface geology shown in these maps comes from data gathered from a variety of sources. These sources include topographic maps, satellite images, and boreholes. Rocks in the field also provide data. A geologic map contains one or more cross-sections. These are constructed by projecting the rock units and other geologic features seen at the surface downward into Earth. To do this, geologists must measure the angles that rock units and structures dip into Earth. The geologic map is a description of the bedrock. Geologists then use the map to interpret the area's geologic history. The scientific study of rock layers is called stratigraphy. This involves the application of several basic principles which follow. Some of these principles might seem like common sense to you. In a way, they are. However, when they were first developed long ago, they were revolutionary. They advanced how early geologists thought about the geologic record. They provided powerful tools for analyzing the relative ages of rock layers and structures. Principle of superposition. Younger sedimentary and volcanic rocks are deposited on top of older rocks, as shown in Figure 1 on the previous page. Principle of original horizontality. Sedimentary and volcanic rocks are laid down in nearly horizontal layers. Principle of lateral continuity. Sedimentary and volcanic rocks are laid down in layers that are usually much greater in lateral extent than in thickness. Principle of cross-cutting relationships. If one rock unit or geologic feature cuts across another rock unit or geologic feature, it was formed later in geologic time. Here are two examples of this principle. If you see a rock unit cut by an igneous intrusion, such as a dike, you can be sure that the dike is younger than the rock unit. So we're going to look at Figure 2. Let me scroll down a little bit. Figure 2 illustrates the principle of cross-cutting relationships. Which rock unit shown in the photograph is the youngest? Okay, so now we're going to read about this. Principle of cross-cutting relationships. If one rock unit or geologic feature cuts across another rock unit or geologic feature, it was formed later in geologic time. Here are two examples of this principle. If you see a rock unit cut by an igneous intrusion, such as a dike, you can be sure that the dike is younger than the rock unit. Okay, so that's illustrated by this figure. So this is younger. So this part cutting through, whoops, let me scroll down. So the dike cutting through is younger than the surrounding rock. All right. If you see one or more rock units cut by a fault, then you know that the fault is younger than the rock units. See Figure 3. Figure 3, after intruding into the surrounding granite, this dike was offset by a fault. So here's the granite, that's the oldest, okay? There's the dike cutting through, that's the second oldest. So the granite is the oldest. The dike cutting through happened next. And then the youngest feature is when the fault cut through, because the fault cut through both. So we know the fault is the youngest. Okay. All right. Unconformities. There's another important concept to think about when trying to interpret the geologic history of an area. Successions of sedimentary and volcanic rocks are deposited on an earlier rock surface. The change from one rock unit to another is usually abrupt. It occurs across some surface or narrow zone of change. This surface or zone is called a contact. The contact between that earlier rock and the younger layers is called an unconformity. It is important to note that for some period of time, nothing except perhaps erosion was occurring on this surface. Some period of geologic time was not recorded at the surface. The missing time might be as short as thousands of years. However, it is usually much longer. It can be hundreds of thousands to many millions of years long. At some unconformities, more than 1 billion years of Earth history is not recorded. Figure 4a shows an unconformity in which the older underlying rocks are at a different angle than the younger overlying rocks is called an angular unconformity. So figures 4a and 4b show two common kinds of unconformity. In figure 4a, younger sedimentary rock is resting on an older one. The older one was folded, then it eroded down. This occurred before conditions changed and more sediment was deposited. In figure 4b right here, let me get rid of some of these windows so we can see this. Okay, in figure 4b, a younger sedimentary succession is resting on an intrusive body of granite. The granite was placed deep in earth. Erosion later wore down the land surface to the level of the granite intrusion. Then conditions changed for some reason. Sediment was deposited on the previously eroded surface. These examples show, let me scroll down a little bit. These examples show that an unconformity can be very helpful in interpreting geologic history. So in figure 4b, an unconformity that develops when older igneous rocks were exposed to erosion before sedimentary rocks covered them is called a nonconformity. The use of fossils in dating geologic successions. As you have read, fossils represent the remains of once living organisms. Most fossils are the remains of organisms that are extinct. This means that they are no longer living anywhere on Earth. Fossil records help to mark the divisions within the geologic time scale. These divisions are largely based on the appearance and disappearance of specific species of fossils. Scientists use the fossils to find information about the ages of rocks. To help them do this, they have developed the principle of faunal succession. This states that because life on Earth has changed through time, the kinds of fossils found in rocks of different ages will also differ. This means that when the same kinds of fossils are found in rocks from different places, then those rocks are the same age. Therefore, if the range of fossils contained in a rock are known, then the age of that rock can be determined. So figure 5 shows species of mollusks used as index fossils to identify specific periods of geologic time. So you have the era, second column is the period, third column is how many millions of years ago, and then you have your index fossils, meaning that if you just as a hobbyist or as a professional finds one of these fossils as you're hiking around or walking around, then you can use this chart to locate the fossil that you found, and then you can trace that back on the chart to how many millions of years ago that fossil was living. You can trace it back to the period and even the era, okay? So be on the lookout because we do have many because Beloit and Rock County and southern Wisconsin and northern Illinois are part of an old shallow sea. We do have a lot of these sea creatures, and a lot of them are actually embedded in limestones. Like if you go to Devil's Staircase in Janesville, or if you see any other limestone outcroppings in southern Wisconsin, take a look at that limestone because a lot of these fossils are embedded in that limestone, in that sedimentary rock. Okay. Rock County. Rocks in Rock County and fossils in Rock County. Okay. Figure 5. Species of mollusks used as index fossils to identify specific periods of geologic time. So that's kind of a cool chart. And you have this PDF in your Google Classroom to refer to, and you can also pause this video and take a screenshot if you'd like a copy of that for yourself. Fossils that lived for narrow time spans are very important. They can be used to indicate very specific periods in geologic time. These are known as index fossils. Examples of index fossils are shown in figure 5. And I think that was what we just looked at up here. Yep. Okay. All righty. The presence of a key index fossil in a rock reveals the date of the rock. For example, the trilobite Paradoxus pinus indicates, they said trilobite. Yeah, we have these in Wisconsin. Okay, we do have those fossils. All right, the trilobite Paradoxides pinus indicates that a rock was deposited between the Ordovician and Cambrian periods. Most often, rocks contain several fossils without an index fossil. In that case, scientists look at the overlap in the age ranges of the fossils. They try to find the period when all the fossils existed at the same time. In this way, they are able to narrow down the ages of these rocks. This approach to finding the relative ages of rocks is called biostratigraphy. This approach to finding the relative ages of rocks is called biostratigraphy. Figure 6 shows the history of 5 fossils. It illustrates how biostratigraphy is used to determine the age of ranges of 3 fossil-bearing rocks. So in Rock A, they found fossil A and fossil C, so they know that Rock A is from, this period. These are the ranges that it could possibly be. And then you line up, and there's fossil A, so you line up that it existed during this time, and then a little bit later, it picked up fossil C. Hold on, because that doesn't have the millions of years. Hold on. Yeah, so it gets older as it goes further down. So as you go further down, it's older as you go further up. So it picked up fossil A first, because that's the oldest, and then it picked up fossil C. So that's this. That's Rock A. And then you guys can see how Rock B has fossil B and fossil E. So fossil B is the older fossil, so Rock B would be dated as the older one. What's the oldest fossil in Rock C? Well, fossil D's in there, fossil B's in there, fossil C's in there. Fossil C existed during this time. So because it has fossil C, it could have existed any time within this period. But then the fact that it has fossil B kind of narrows it down a little bit to existing within this period. So it existed sometime between here and here, because we're just lining up those arrows of all the fossils that are included. Okay. So you guys see how important those charts are. All right, figure 6. A hypothetical example of the age range of 5 fossils. The ranges are fossil A is, let me move this up. Fossil A is Silurian to Ordovician. Fossil B is Cretaceous to Devonian. Fossil C is Quaternary to Ordovician. Fossil D is Jurassic to Silurian. So how are they getting all this stuff? Okay, so when they say fossil D is Jurassic to Silurian, how are they getting that? Well, they're looking at fossil D, and they're seeing that it's Jurassic to Silurian. So they're just using that arrow. Okay, they're using the arrow to see when it lived. All right. And really where it's found, which helps the scientists determine when it lived. Okay. Fossil E is Tertiary to Jurassic. The age ranges of the rocks are Rock A is Silurian to Ordovician, Rock B is Cretaceous to Jurassic, Rock C is Jurassic to Devonian. We talked about that earlier. Okay. Species that make good index fossils have the following characteristics. They need to be well preserved so they're easy to find, distinctive body shapes that make them easy to recognize, large populations so they are abundant, a widespread distribution that allows for distant locations to be compared, existing for relatively short periods of time that indicate precise ages. Yeah, there's a lot of cool stuff in the limestone around here. Okay. All right. Yep, we went through this. Okay. Index fossils are often found. What? Index fossils are often from animal species that had hard exterior bodies. Also, the best index fossils are from animals that lived mainly on or near the seafloor. The water would also need to be quite calm. For these reasons, the most common index fossils are marine mollusks. Figure 5 shows many of the different kinds of mollusks used to identify the ages of rock layers. For example, in sedimentary rocks from the Jurassic and Triassic periods, the flat spiraled shells of ammonites are common. They evolved very rapidly. They could also be found throughout the oceans during these periods. As a result, they are very useful for comparing the ages of rocks on all the continents. Earlier than the Paleozoic era, the trilobites achieved similar success. They are an index fossil for sedimentary layers dating back to 520 million years. And we actually found one when we were building a house in Oconomowoc, Wisconsin, when I was growing up. And they were digging the basement out, and they found a trilobite. So that'd be a seafloor. That'd be a seafloor mollusk, marine mollusk. So at one time, where our basement is now, that was at one time a seafloor. All right. It's an amazing planet. Okay. Fossils can be used to find the relative age of the rock layers in which they occur. Then the age can be correlated to other sequences containing similar layers. Following this approach, a longer sequence can be constructed from many smaller sequences. Look at Figure 7. The oldest rocks in Outcrop B appear at its base. The mollusks they contain are the same age as those at the top of the outcrop. Therefore, the lower layers in Outcrop A may provide insight into the geologic history below the oldest layer of Outcrop B. On the other hand, Outcrop C can be correlated to the top of Outcrop B. It reveals a younger part of the stratigraphic column. Biostratigraphic correlation of rock layers from different places using the ages of fossils found within the layers. Okay. And then the correlations they're seeing, they're calling that a correlation because they're seeing that there's similar fossils. All right. There are a number of different reasons scientists want to know the age of rocks. For instance, this information is used to predict the locations of coal and minerals. It is also used to reconstruct the geologic history of an area. For example, scientists have correlated rock layers in Chesapeake Bay on the mid-Atlantic coast. This has helped them determine how this bay was formed. They determined that 35 million years ago, a meteorite hit the area. See Figure 8. Okay, right here. It created a massive impact crater. They found that before the impact, sedimentary layers extended laterally for long distances. After the impact, oh, that's in Virginia. Okay. After the impact, hold on. Where am I? I'm looking at the map, so hold on a second. After the impact, these sedimentary layers were disrupted. And that's displayed in this figure. Okay. So this is the overhead view of the impact site of the crater. And then this is the side view of the crater. All right. Let me back up. For example, scientists have correlated rock layers in Chesapeake Bay on the mid-Atlantic coast. This has helped them determine how this bay was formed. They determined that 35 million years ago, let me scroll down so you can see both figures. They determined that 35 million years ago, a meteorite hit the area. It created a massive impact crater. They found that before the impact, sedimentary layers extended laterally for long distances. Right here. After the impact, these sedimentary layers were disrupted. Okay. They were disrupted by several faults along the rim of the crater. Using index fossils, they observed that along these faults, younger layers were moved against older layers in the sequence. The main impact structure is now buried beneath sediments in the bay. So Figure 8, the meteorite impact site that formed the Chesapeake Bay. And Figure 9, faults along the rim of the crater disrupted the sedimentary beds. The original stratigraphic sequence was reconstructed using fossils.